Hello, this is section 2.3 from chapter 2. It is about calculating limits using the limits law. So the objective of this lecture is to understand and apply the limits law to compute the limits of some functions. Here are the laws. So basically, if we have a limit of f of x when x approaches a is given, and also for the same for the function g, both of them exist, and we take a constant real number c, then we can add any two functions and compute the limit of the sum, which is equal to the sum of the limits as stated in law number 1. Also, we have the same thing for the difference. So the limit of the difference is equal to difference of the limits. If we have a constant which is independent of the variable x, then we can take out of the limit the constant c. That's the rule number 3. Number 4, the multiplication also, we can separate the limits. So a limit of the product is the product of the limits. The only attention here is for the rule number 5. So here we have to be carefully of the division, since here we have, as you can see, we have a division by g of x. So we should have this limit not equal to 0 to make this rule available. Number 5. Okay, so we will be carefully of the division by g of x. So this is inwards the rules that we saw in the previous slide. So as we said, for example, rule number 1 is the sum law. So the limit of the sum is the sum of the limits, and so on for the other rules. Okay, let's take example 1, and we have here graphs of two functions, f and j. F is in red and j is in blue. And here we have to pay attention to the corresponding graph for each function, okay? And we want to compute the limit of f of x plus 5gx when x approaches -2. So we will use the rule of the addition of the limit. So this is equal to, in fact, limit f of x when x approaching -2 plus 5 limit g of x. Okay, I will detail this, make details for this first example, then I will compute directly for the next ones. Okay, so the additional rules give me this equality, and now I have to compute this limit, okay, in red, in green, and the other limit, which is this one, okay, and then make the addition and multiplication by 5 for the second one. So clearly the limit of the function f of x when x approaches -2, so I will take x equal to -2, which is here, okay, this is -2, and then go to the graph of f and see what is the corresponding y. If we see here, right to -2, left to -2, both of them, they meet at the same point 1, so the limit exists and it is equal to 1. So this value is in fact 1. Then limit of g of x at the same point, so I have to go to the graph of g, starting from x equal to -2. So here is the graph of g, and I see clearly that right, left, they meet at the same point, and the value of the limit is -1. So I can conclude that this is equal to 1 plus 5 times minus 1. This gives 1 minus 5. That means minus 4. Okay, and the example A is done. Okay, now for example B, we need the limit of the product when x approaches 1. 1 is here. Limit for f is exist and does exist, and it is equal to 2. And limit of chain is right here, left here. They don't meet at the same point, so the limit of g of x for question B does not exist. So the whole thing does not exist. Okay, all these does not exist, since limit of g of x when x approaches 1 does not exist. Okay, so next example, C. Here we want to compute limit f of x over g of x when x approaches 2. So 2 is here. Okay, the function in red is the f. So the limit for f is at the point 1.4. So it is equal to 1.4 over limit of g of x, but g of x is equal to 0. So this, again here, since the denominator is equal to 0, does not exist. Okay, or undefined, we say sometimes. Okay. So, of course, here we will see later that we will take the limit to the right, to the left, and see what happens for this. But it's a little bit early to talk about this. Okay. Here are the solutions of our examples. And now we will go to the power law for the limit. So if we have a power of a function, we can also switch the limit and the power when n is a positive integer. The root law also, we can switch limit and nth root of the function if n is a positive integer. Remember now here the special cases for 8 and 9, the limit of a constant c when x approaches a is equal to c. I had some questions. It seems strange, this limit for some students, so I will explain a little bit why we have that. So if we think of function which is f of x equal to c, what does it mean in terms of graph? That means that I will take c equal to 1 to explain, okay? So this is x and y. F of x equal to c equal to 1, that means it's a horizontal line like that. Let me do it in red. Okay, so this is the function f of x equal to 1. Whatever the x that you take, let's take a here, all the time, right, left, you will get the limit equal to the constant 1. So that's why limit of c when x approaches a is equal to c all the time. Now, what happens for limit of x when x approaches a? This is, in fact, linear. This is line, the first line here. So f of x equal to x. Each time you take a, since this is y equal to x, so the y will be the same thing, a. So the limit will be equal to a, like this in rule 9. Okay. Other limits law, number 10 is also a consequence of what we saw before. So limit x power n is equal to a power n when x approaches a. This is consequence for from the switch between the limit and the power. So And this is preparation for the limit of any polynomial. In fact, x power n is somehow a monomial of the polynomial. Now, for law number 11, we can switch nth root with the limit, but here we need that when n is even, we need that a is positive. Why? Because you remember, for example, the simple square root, the usual square root of x, this is defined when x is greater or equal to 0. Okay? However, if it is cube root, it is defined on any real number. That's why we talk here about a positive or when n is even, to make sense to this function. Okay, but in general, you can switch the limit and the nth root, but you have to ensure when n is even that a is positive. That's it. As consequence from the previous laws, we can write directly that the limit of any polynomial at the point A is the value of the polynomial at A. Same thing for rational, but here we have, since we have division by q of x, so we need that q of A is not equal to 0 to make sense to the limit for the rational function. Okay. We have here, if we have an equality between two functions when x is not equal to a, then necessarily they have the same limit, provided that the limits exist. When the limit exists, necessarily, since we have equality between the function, so the limit is the same. We will work a little bit on example 2. So we start here by example A. The limit of this function when h approaches 0, this is a rational function. Since it is polynomial over polynomial, normally we can substitute h by 0 and see what happens. But when we take h equal to 0 in the expression of the function, clearly we will find here 3 plus 0 squared 9, 9 minus 9, that means 0 over 0. We call this indeterminate case or sometimes indeterminate form. Okay? What does mean indeterminate case for the limits? It means that we cannot decide about the value or the existence of this limit. You have to continue and change the expression of the function. Like that, you remove this indetermination. Okay? So what we will do here, we will expand the square. And it will give 9 plus 6h plus h squared minus 9 over h. The 9 with minus 9 will cancel. Then I will get limit h approaches 0 of 6h plus h squared over h. I can take h common factor. So h times 6 plus h over h. Sorry, it's h, not 6. Okay, this is h. Then I have h approaches 0. Simplify by h here. And then I will get limit of 6 plus h when h goes 0. Now I can substitute the h by 0, since we removed here the indetermination, so I will get 6. And this is the value of the limit for question A. We'll do the same thing for example B, and clearly we will start with the substitution. T approaches 0 of this function, t squared plus 9 minus 3 over t squared. So if I substitute, then root 9 minus 3 over 0, that means 3 minus 3, which is 0 over 0. So again here, indeterminate form. I will try to change the expression of my function. And since here we have a square root, then I will think about conjugate. What is the conjugate? If we have an expression like that, containing a square, then if you have minus between the two terms of the expression, make it plus for the conjugate. If you have plus, then make it minus in the conjugate. So here, since I have minus between the two terms, then I will make the conjugate with plus. So my limit is equal to, between parentheses, root t squared plus 9 minus 3 over t squared. And then I will use another color for the conjugate. So the conjugate is root t squared plus 9 plus 3 over the same thing. Since I don't want to change my expression, of course, keep it the same, just it's a manner to rewrite the same expression. Okay, now here, if you see this numerator, it's of the form a minus b times a plus b. This exactly equal to a squared minus b squared. So no need to expand. Use this formula directly. So it's equal to root t squared plus 9 all squared minus 3 squared. This is my formula from here. Over what it is in the denominator, and I keep it like that. T squared multiplied by the conjugate. T squared plus 9 plus 3. Now in the numerator, I will get for sure a simplification. Then I will have my limit. So it's t squared plus 9 minus 9 with the limit here. T approaches 0. Then plus 9 minus 9 will cancel. And the t squared now it is in factor. So the t squared is somehow here. Okay, I need my pen. So t squared times root t squared plus 9 plus 3. Okay, so t squared with t squared will cancel. Now I can substitute. I have only 1 in the numerator. So it's 1 over root 9 plus 3. Since I replace t by 0, so this will give me 1 over 6. And this is my final answer for the limit. Okay, let's go to the next slide. It is the solution, of course. Now we will talk about the one-sided limits, what we called before the right-left limit. Okay, so when we are right of a number a, that means we are like a plus. That means we are close to a, but greater than a. When we say a minus 1, that means we are close to a, but we are left to the a only. Okay, so the limit in general at the point, exactly at the point a, exists if and only if the limit to the right, limit to the left, they are both equal to the same number, L. Here is the example 3. Look at this function f of x. It is defined in two parts, x greater than 4 or x less than 4. We want to determine the limit at 4. So we will compute limit to the right, limit to the left. So limit f of x when x approaches 4 plus, that means that I am close to 4 but greater than 4. So I will take expression number 1. Okay, and I will substitute. If I substitute, I will find 0. What about limit to the left? And to the left, that means 4 minus. 4 minus, that means expression number 2. And a substitute there, I will find 8 minus 8. That means, again, 0. So the limit is equal to 0 by the right and left. They have the same value. Okay, let's take the try and check example here. So here the try and check is about computing the limit of this function at when x approaches minus 4. Okay, so here for this example, since we have absolute value, we can express this function in two ways. So you have to remember here, and I will share whiteboard. So if I want to compute limit x approaches minus 4, x plus 4 minus 2x. Okay, I can, as I said, I can use the definition of absolute value of x. Remember that absolute value of x is equal to x if x is greater or equal to 0, minus x is if x is negative. Okay? So with this definition, I can express my function as follows. X plus 4 minus 2x if x plus 4 positive, or minus x minus 4 minus 2x if x plus 4 is negative. I will compute now the function. So it will give me 4 minus x if x greater or equal to minus 4. I will write this condition in this way. And I will have minus 3x minus 4 if x is less than minus 4. Okay, so I have right and left for minus 4. And I will compute the right and left limit. Let's call the function f of x. So x approaches minus 4 plus. I will use this expression. Okay? So it is equal to limit x approaches minus 4 plus, and my expression was 4 minus x. That means 4 plus 4, which is equal to 8. However, limit f of x when x approaches minus 4 minus. So I will use the second expression, this one. Okay, so here it's limit x approaches minus 4 minus of 3 minus 3x minus 3x minus 4. Now I substitute x with minus 4, it will give 12 minus 4. That means again 8. So you see here that limit left equal to limit right. My conclusion is that the limit of f of x when x approaches minus 4 is equal to 8. Okay. Now the next example is the function, let's call the function g of x equal to 2x minus 1 over absolute value of 2x cubed minus x squared. We will try to simplify a little bit this function. So it is equal to 2x minus 1. Inside the absolute value, I can put x squared common factor. So x squared 2x minus 1. And I will use the property of absolute value, which is product of absolute value of product is product of absolute value. So it's absolute value of x squared times absolute value of 2x minus 1. But since x squared is positive, it's non-negative in fact, so I will remove the x squared, the absolute value from x squared. So it's x squared times 2 absolute value of 2x minus 1. Okay, now I will use the definition of the absolute value. I know that 2x minus 1 is equal to 2x minus 1 if 2x minus 1 is positive, that I will write like that, x greater or equal to half. And minus 2x plus 1 if x less than half. Okay? So my function g of x will be equal to 2x minus 1 over x squared times 2x minus 1, because I substitute here the value of the absolute value, which is equal to, if we simplify, 1 over x squared. But this is the expression in the first region, so if x is greater than half or 0.5. And the second one is 2x minus 1 over x squared times the opposite, minus 2x plus 1. Okay, so which is equal to minus 1 over x squared. Why? Because you put minus outside in common factor, so it will become 2x minus 1, and then you simplify. Okay, so you can write it in this way, 2x minus 1 over minus x squared times 2x minus 1. In this way, you simplify and you get minus 1 over x squared. And this is it in the second region, so x less than 0.5. Now we want the limit when x approach 0.5 minus, so it means it is in this region number 2. So the limit f of x when x approaches 0.5 minus is equal to limit minus 1 over x squared when x approaches 0.5 minus. So it is equal to minus 1 over 0.5 squared, that means 0.25, which is equal in final minus 4. Okay, so that's the result for the second limit. Now I will go back to the slides. Okay, and then I will continue to the concept of the squeeze theorem. What is the squeeze theorem? This theorem says that if we have comparison between two functions, f and j, let's assume f less than or equal to j of x, then the limit will be in the same order of inequality. Okay, so that's the first theorem, but the squeeze theorem will need double inequalities, in fact. Okay, so if we have a function g of x, which is between another function and a second function, and you know that this function to the right goes to L when x approaches a, same for the one to the left, so necessarily this limit is L. Okay, so the conclusion comes from here and here, so it will give the limit of g of x is equal to L. So we say that this is go to L, this is go to L, the conclusion that this one goes to L also necessarily. That's the squeeze theorem. Okay, in terms of graphs here is the function j, and assume that locally close to a, the h is greater than g, the f is less than g, so they have the same limit, so necessarily the one in between them will have the same limit. Look at this example, and we will apply here the squeeze theorem. So we want to show that this limit is equal to 0. We know from semester 2, let's say that any sign, in fact, sign of any number is between 1 and -1. Remember that the range of sine, cosine are equal to -1 and 1. That's why we can bound the sign between -1 and 1. Now, if we have inequality, then we can multiply by a positive number without changing the order of inequality. So I will multiply here by x squared. Okay, so I will get minus x squared less than or equal x squared sine 1 over x less than x squared. Now I want the limit when x approaches 0. This one, when x approaches 0, goes to 0. This one also goes to 0 when x approaches 0. So necessarily this one goes to 0 when x approaches 0. This is by application of the squeeze theorem. Okay. Good. Let's finish this lecture by the try and check, and here same order of idea. We will apply the squeeze theorem, same process. Cosine of anything is between 1 and -1. X fourth is non-negative number, so I can multiply the inequality without changing anything. So it will give minus x fourth less than x fourth cosine 1 over x less than x fourth. Then I want the limit when x approaches 0. This one will go to 0 when x approaches 0. This one also will go to 0 when x approaches 0. So the conclusion that this one goes to 0 when x approaches 0 by the squeeze theorem. Okay. That's for the first example. The second example is also application of a squeeze theorem, but we need to bound, of course, the sine function using the range of sine. So I have that sign of anything is between 1 and -1. Okay, now I need to compute the exponential of the sign. But you remember from semester 1 that the function exponential is, or we call it usually EX. This is increasing function, okay? So it will keep the same inequality for them. Increasing, it means that if you have A less than B, then exponential A is less than exponential B. That's the meaning of increasing. So I will apply this to my double inequality here, and it will give E minus 1 less than E sine pi over X less than E power 1. Then multiplication by the root X here, which is non-negative. Okay, so I will have, without changing the inequality, root X, and I want the limit when X approaches 0. This one will go to 0, 0 plus. Here it is important that the 0 plus, because the root cannot be defined for 0 minus. Remember that. Root X and define it for 0 minus. Okay, this is by the way. So this one goes to 0 when X approaches 0. So my squeeze theorem will give that this limit is 0 when X approaches 0 plus. Okay. And by that, we are done for this lecture. Thank you so much.